Hey, geometry students, welcome to lesson 4. We're going to be talking in this lesson about postulates and theorems about points, lines, and planes. We're going to start off with a few definitions, and then we're going to start talking about some postulates, remember, which are statements that require no proof. They're not proven, but we just accept them as true. They're so intuitive that they just make sense even without proof. And then theorems, we haven't learned any theorems yet. In this lesson, we're going to talk about some theorems. Theorems are statements that have been proven. We're actually going to prove the theorems that are in this lesson later on in this course. Okay, but first of all, we would have to learn how to do geometric proofs, and that doesn't come up for a little bit yet. So we're going to start by just learning the postulates and theorems, and we can use those postulates and theorems to explain things that we see in geometry. But first, let's start off with some terms. The first term we're going to learn today is perpendicular lines. These are lines that intersect at a right angle. So here I have a cube. We assume that a cube has all right angles. Anywhere two segments come together, they come together at a right angle. So I could say in this cube that segment AD or line AD is perpendicular to line DC. And I could also say the same thing about segments because lines contain segments AD and DC. If I were going to write that in a notation, it would look like this. Notice what the perpendicular symbol looks like. And this reads segment AD is perpendicular to segment DC. Now I know technically I'm talking about perpendicular segments when the term was perpendicular lines, but again, the line that contains AD, so line AD would also be perpendicular to line DC. What about parallel lines? Now, I have to add an extra word to parallel lines. I have to add the word coplanar. Because keep in mind, for perpendicular lines, they intersect. Perpendicular lines intersect. And by definition, any lines that intersect are coplanar. Parallel lines don't have, like, when I have lines that don't intersect, they don't necessarily have to be coplanar. But parallel lines are coplanar. So let's take a look at AD and BC. AD across the top, BC across the bottom of this cube. Those are parallel lines because they are in the same plane. I actually have that plane drawn. It's plane ABD, the front plane of my cube. They're coplanar, but they don't intersect. They run in perfectly the same direction. So therefore, we would say that they're parallel. This would be the notation for parallel lines. AD is parallel to BC. And again, that could be line AD or segment AD being parallel to segment BC or line BC. All right, parallel planes are planes that do not intersect. I don't need any other language there because if planes do intersect, in any planes do intersect, they're not parallel. And if planes don't intersect, they're automatically parallel planes. All right, and then finally, skew lines exist. Skew lines are non-coplanar lines that don't intersect. So let's take a look at an example of some skew lines. That would be like line AD and line FG. I'm just going to overlay these lines on top to make it more obvious where they are. Okay, so line AD I made bolder and thicker because it's in front, it's closer to us. Line FG is a little narrower because it's in back. Notice that AD is not in the same plane as FG. There's no plane that I could draw that would pass through both of those lines. And they don't intersect. AD misses line FG. It's in front of it. These would be called skew lines. They're non-coplanar, but they still don't intersect. All right, those are the 4 terms I wanted to introduce at the beginning. Now let's dive into some postulates. Most of these postulates are so self-evident, I'm just going to introduce them and move on. We're not going to spend a lot of time talking about any of these. So we've already learned 4 postulates in geometry. We're going to keep counting up with postulate 5. Postulate 5 states that through any 2 points, there's exactly 1 line. Another way to think about this, there's no way I can connect 2 points with a straight figure other than the exact 1 line that connects them. And any other figure that I could connect 2 points with is not a line because there's just 1 line. So if I draw the line that connects 2 points and I try to make another figure that connects those 2 points, there's no way to do it. There would be no second figure. That's postulate 5. Next, we're going to read theorem 4.1. Now notice that for theorems, we haven't learned any yet, but this one's starting at 4. What that means is it's in chapter 4 in the textbook, and it's the first theorem in chapter 4. So theorems in our textbook are labeled by the chapter they appear in. Theorem 4.1 states that if two lines intersect, they intersect at exactly one point. So let's think about line AB and BC up here. If I have line AB and line BC, the only point they'll intersect at is point B. And then on the left side of that point, in the bottom, they continue to move away from each other, so they'll never intersect again. And the top and the right, they continue to move away from each other. Now keep in mind, we're going to prove theorem 4.1 in a future lesson. For now, we're just going to leave it as its own statement. Two lines intersect, they intersect at exactly one point. Hey, I just want to point out, notice it also says if there are examples of two lines that don't intersect, that wouldn't be subject to this theorem. That would be parallel lines or skew lines. All right, what about postulate 6? Through any three non-collinear points, there exists exactly one plane. Notice we have the qualifier word non-collinear in there. That means that if 3 points are on the same line, there's an infinite number of planes that contain that one line. But if we have 3 non-collinear points, C, B, D up here, there's just that one plane that contains all 3. I can't draw a second plane that contains those 3 points other than the first one that I drew. Okay, and then on to our next theorem. Theorem 4.3, if two lines intersect, there exists exactly one plane that contains them. That would be line AD and DC up here. I could picture this one plane contains those two lines, but I can't picture any other plane that would contain those two lines and still be a plane. Maybe some curved two-dimensional figure can, but not an actual plane that has to be flat. Okay, so here we have a start to some postulates and theorems that we accept are true. Let's take a look at another one. Theorem 4.2. I did this one out of order. I apologize. I'm just going to leave this in the video, but I should have done 4.2 before I did 4.3 because this is the second one that comes up in chapter 4. If there is a line and a point not on the line, then exactly one plane contains them. I could have probably come up with some reason why this would be after the other one, but oh well. So you picture a line, AB, and then just point C. Now notice that it's really the same thing as line AB and line BC, because all of those points in between B and C are going to be contained on the plane that contains A, B, and C anyway. But that's theorem 3. If we have a line and a point that's not on the line, there's going to be exactly one plane that passes through all 3. All right, continuing onward. Postulate 7. If two planes intersect, then the intersection is a line. Here we see that plane ABC intersects plane HBC. Okay, so this front plane intersects the bottom plane. What do they intersect at? They intersect at a line, line BC. All of the points on line BC lie on both planes. That's really the key there. All right, postulate 8. If 2 points lie on a plane, then the line containing the points lies on a plane. So think about AC. Line AC lies on plane ADC. Okay, this diagonal line here. Does that entire line lie in plane ADC? Why, yes, it does. If 2 points lie on a plane, then the line containing all of the points lies in the plane as well. Now keep in mind, if I have 2 points in a plane, there's actually an infinite number of planes that could contain those 2 points. Also remember, there's an infinite number of planes that can contain an individual line. So those are related concepts there. And then finally, there's postulate 9. Postulate 9 states that a line contains at least 2 points, a plane at least 3 non-collinear points, and space contains at least 4 non-coplanar points. These are statements that we've been making all the way through geometry so far, so there's nothing new here. This is just stating it as a postulate so that we can use it later for proving things in geometry. And that's lesson 4. We're going to go on to some lesson practice after this.